And we made it. Welcome back, folks. I think this is our first Monday in like 3 weeks or something. So good on you for all making it in today. Probably the biggest announcement we want to talk about today is just talking about the upcoming exam next Monday. But any questions folks have so far? Okay, well, the sample exam documents here have been finalized. Really, there was just said revision or early draft just in case it was going to be a section short or a section longer. But somehow it's got the right number of sections. Exam one goes from chapter one, pretty small bit of work we did there, really just getting started. And it goes up to sections 2.1 through 2.5. Some of these are a little bit smaller, some are a little bit bigger. We're about to finish off section 2.5 today, or possibly early Wednesday's class. So that's going to be the entirety of exam one. And if you take a look at both of these documents, you'll get a good feel for what's on the exam. Also, you'd want to take a look over your quiz one, your quiz two when it's graded and returned. We'll have a third quiz as well that's posted here just for helping out prepare for the exam. Other things that are from the syllabus, but we talked about very briefly on day one, are that all exams are closed book. All exams will require a TI-84 calculator or equivalent. So if you've discussed a Casio model that's working for you, of course, you're welcome to bring that. I'll have some spares calculators just in case something goes wrong with yours, but it's always good to use the one that you're just more familiar with. People have already observed in class there's like 5 different versions of this particular calculator. Some of them have different looking display. All the buttons and stuff are the same, but they feel different. So if I give you a different calculator, that's not a new variable you want to change on exam day. Other big thing about the exam is they're all open notes. So you can have one single 8.5 by 11-inch page of notes. That's a page of notes of about this size, for example, ordinary printer paper. And there can be anything you like on it. So whatever you feel like is going to support you through exam one. Some people put lots of definitions, ideas, those kinds of things, excerpts from the notes. Anything you like will be that you think is helpful, you're welcome to bring. I'm not going to collect your page of notes. So at the end of the exam, you'll just take it with you, probably put it in a drawer and pull it out again once final exam comes around. You might want to look over that same information again when you're studying for the final. So that's how the exam will go. It'll be in this classroom. It's a 70-minute exam, but I'm not going for a super long one. It's going to be about 50 to 55 minutes, I'd say, for the average student, with built-in time for double checking your answers and that kind of stuff. Any questions at all, folks, about the upcoming exam? Okay. Once you get through exam one, it becomes a little bit less stressful. Kind of the idea with, yeah, go ahead. It is front and back, yeah. So both sides, one page, and then you're all set. Absolutely. That's a great question to always clarify. And other thing to keep in mind with the upcoming exam is everything we've been doing all along in class is pretty much exam material. Occasionally we've talked about examples that don't fit on exam, and we literally said, doesn't make a good exam question. This is us illustrating a definition or something like that. So these problems are going to give you a better idea of what really looks like an exam question. It's pretty much the same kind of major notes that we've been going through. For example, this could be an exam question. And this is the one that you want to be extra ready to go. Learning your calculator and knowing how to use your calculator is part of the exam. So if you could do parts A through E on your calculator, then you know all the important statistical functions for the purpose of this exam. And I think that's pretty much my announcements for today. Any other questions so far before we get started? Okay, well, we're on example one of section 2.5. This is the cutoff section. So we still have to move forward on Wednesday when we're beyond 2.5. We'll be getting into chapter 3 material. But for the purpose of the exam, this is where it all ends. I don't like to cover material on Thursday and then just turn around on the next Monday on exam. I feel like that's just too short of a turnaround. So it's usually going to be something like this, finishing off a section, and it's the last one on the exam. And by the way, another good habit, sorry, I keep reminding myself of reminders. Always you want to check in your grades on the Canvas website. I updated these on Sunday after grade quizzes, so you should have your Courage grade coming from MyLab statistics pulled in, as well as your quiz grade. So they're now both equally weighted according to the syllabus. giving you a good representative idea of where you're in the class right now. And finally, aside from all that, here's where we left off. We're on example one. We really finished it, but just like many things in statistics, there's so much to talk about. In the last section 2.4, we were looking into histograms and placing things like where's y bar, where's the median, to just get a feel for what these values are saying. Median at 26.5%. This was healing rate. 26.5 micrometers per hour is about here. The sample mean is slightly lower at 25.7, right around here. And all that's telling us is that this is pretty symmetric data. Slight skew to the left due to this region right here, but they're pretty close values. And we have a good idea of what they're trying to say now. More challenging still, though, is when you throw in more statistics. We had 3 more statistics to take a look at is to see what all they're saying at once. So we'll spend a little bit more time on example 1 just to visually see what are our new statistics trying to say. These last 3 parts C through D are the new ones, and they measure either the section title, spread, or you could say synonymously, they measure the variability. Let's say it both ways. Measures spread and how can I say that's equivalent? Let's just put a hash through there just to say or variability. So that's what they're supposed to do. The range is not too hard to see, right? The range is just the distance. You go from the minimum value, which is 11, all the way up to the maximum value, which is 40. And that's all the range is telling you. The length along the region your data occupies. The next 2 are slightly more challenging. We mentioned what this is trying to say, the interquartile range. But it's one thing to write it down, another thing to actually see it. So let's take this down below maybe to right around here and take another look at what's going on with the so-called interquartile range. We'll do it again for the standard deviation S. So we had IQR is 11, S is 8.3. And if we can see what those both statistics are trying to say, it gives us a little bit more meaning. I mean, at the moment, they're just numbers in micrometers healing rate per hour. So they put down here, S equals 8.3. On this one, IQR for interquartile range equals 11. Let's start with the interquartile range. That one's a little bit easier to see. Any questions first at the moment? Okay, to get the interquartile range, just like what this was before, it's still a range, but we're not going from max to minimum. That's a pretty blunt way to measure how things vary. We're going for quartile 3 to quartile 1. So quartile 3 in our data was 33. So up to here is Q3. Quartile 1 was 22, so that's up to here. So here's quartile 2. And the interquartile range is this length. The way to kind of understand what this is telling us is we just need to recall what is another way to say quartile 3. It was the 75th percentile. And that just tells us if you call this the 75th percentile, then 75% of the observations are below 33, 25% of the observations are above. Likewise, quartile 1 is the 25th percentile. And so same issue on this one. It's telling us 25% of the observations are below 22. Looking at actually visually, it looks believable. This is by area. It's saying 25% of the area is below quartile 2. 75% of the area, all of this stuff, is above it. Likewise, same idea over here. Quartile 3 being in that position says 25% of the area there, 75% of the area full on to the left. So now all the interquartile range is trying to measure is the length of the central 50% of observations. So in other words, we're saying half of our data set are between this number, 22, and this number, 33. And that's how spread out they are. It occupies a length of 11 to capture the central half of your entire data set. So that's the measure IQR. Kind of a fancy way to do it, but if our data is skewed enough, then it's a good measure because it's robust against skewing. Not all of our statistics are. We talked about the sample mean Y bar being influenced by outliers and severe skew. It gets pulled in that same direction. And it gets even worse for the standard deviation, it turns out. In fact, if we look at the formula for the standard deviation, we find that S is defined in terms of the sample mean Y bar itself. We'll do a calculator just to see how that goes. But if Y bar is already biased, this one becomes even more biased because it's the square root of the sum of the deviations squared. That's a mouthful, but we'll calculate by hand just to see what all that means. It's a little bit more challenging to see what S is doing at all in this data set, but to get a readout on it, we need to center Y bar. It's at 25.7. So let's just copy that in here for reference. And now this is what we can do. Our data is at least roughly symmetric. It doesn't work if it's severely skewed, but for this, yeah, it'd qualify. It is at least roughly symmetric. Go to where the mean is, 25.7. Doesn't hurt to connect that thought, is the mean. It's about right here. Here's Y bar. S at 8.3 is the standard. And by the way, if that feels like you're writing a lot every time you're doing standard deviation, this is a pretty decent abbreviation. STD for standard. DEV for deviation will be a common one we'll use in the notes. And now let's look in the calculator what we can do here. Let's go a distance of one standard deviation away from the mean. That means we're going to put down two numbers, and this is quite a lot as well, right? Go a distance of one standard deviation away from the mean. Which direction? Both directions. We want to take the mean. Let me clear this out. Turns out hitting clear will get that out of there. Take the mean 25.7 to go a distance of one standard deviation, add one standard deviation to it, plus 8.3. And we get this figure, 34. So we go to here. This is value 34, which is going to be Y bar plus S. So that's adding one standard deviation. And then we go the other opposite end, go Y bar minus S. So in the calculator, 25.7. Now subtract 8.3. We get 17.4. So we're about here, roughly there. So this is 17.4. And that's equal to Y bar minus S. So when it says go a distance of one standard deviation away from the mean, we're going from here all the way to here. And that contains, well, pretty much most of the data. So that's pretty much what the standard deviation is going to do if your data is roughly symmetric. Let's add a note above for, let me fix that real quick, for data at least roughly symmetric, approximately, and this is a rough approximation, but let's still go with it. there's really two approximations, the rough symmetry here. The more perfectly symmetric this is, the better our approximation next. We'll say approximately 68% of the data is within one standard deviation from the mean. The mean being y bar, standard deviation being s. And so if we go all the way out here, 17.4, subtracting the standard deviation from the mean, y bar, go way out here, y bar plus s, from here to here, all of this is approximately 68% of the data. I'm trying to find a color that shows up. And so that's all the standard deviation is trying to tell us. If we're reasonably symmetric enough, then that's a distance as well. Just like this is a distance. It's the distance that the central 50% occupy as a range. S is the distance that approximately 68% of all your individuals are going to lie in a range as well. Different kind of range. Later on, this becomes some other kind of rule called the empirical rule, or I like it this version, the 68, 95, 99.7 rule. The 95 part is if we went 2 standard deviations, minus 2 plus 2, that's 95% of the data. 99.7 part is if we went 3 standard deviations, minus 3 and plus 3, that'd be approximately 99.7% of all the data. For the moment, this is all stuff that comes back in chapter 5. Reason we're looking at just this part, 68%, is when you calculate S, it's hard to say what you even did. This is what we did. About most of the data, nearly 70%, 68 approximately, is within one standard deviation, subtract or add S, from the mean. A lot of words to say that, but does that kind of make sense how those ideas connect? Okay, for the moment in the notes, we're pretty much just calculating these things. We have to know that IQRS measures the spread, or like we said up here, variability. We also know from connecting the dots with the last section, these two things measure the center. So lots of different statistics to take a look at. These notes are meant to kind of summarize a little bit more what's going on. And we'll calculate S one more time, well, 2 more times, once by hand to get a better feel for what's going on in the formula, and then again by calculator, the way we would do it on a quiz or exam, or even on a homework problem. But any last questions, folks, on looking at these 2 measures of variability? Okay, so kind of in a nutshell, what we did was we went from this one, the range does measure variability, but bluntly, it's just the length from the minimum up to the maximum. And if there's a big outlier there, your range just blows up. It's unfortunate. It becomes not a great way to say where the data concentrates, how spread out is it in the concentrated region. This does a better job. If our data is really, really skewed, it's okay. This is still going to tell you where the central 50% is each and every single time. So it's a great, robust statistic against skewing. But we prefer to use S to measure variability, the standard deviation. It's used in a lot of the statistical procedures that are easy to calculate and are the most powerful. So when our data is at least roughly symmetric, we'll often go for S, the standard deviation. So aside from all those things, next thing we're going to do is, and we're only going to do this once, just to get the idea of what the standard deviation is doing, we're going to calculate by hand using these 4 observations here and only 4. We might as well call up the formula just to remind ourselves on how it goes. Here it is. That's a weird screenshot. Let me try again. So here's our formula. And again, it's hard to look at really. If you have to calculate by hand, we can make that work. Or you could just break it down into these 3 different columns in the table we're seeing here. So that's how we'll approach it. And just because this didn't make it into the notes, This part here, S squared, is the variance. So we have a random sample using the following 4 pieces of data. And this is kind of like just a reminder, you don't have to do this on quizzes. It's really painful. Doing this on an exam is going to make it really hard to complete the exam on time because you're probably going to have like 12 pieces of data, not just 4. So this is just us understanding the formula a little bit better. So we have a random sample of 4 observations. We would like to calculate the mean, the sample variance, that's S squared down below right here. It doesn't hurt to color code it already. And the sample standard deviation by completing the table. Another thing this is doing is it's a sell on why we like the calculator, because it's a tough process. We want to round intermediate computations to 3 decimal places, just so we get as accurate an answer as possible. And then we'll be confident when we round our final answer to 1 decimal place, it's somewhat accurate. Sample standard deviation is going to be our last answer. Everything else is just kind of like a computation in the middle. So looking at these formulas, they're kind of mysterious, right? There's y1, y2, y3, and so on. This says yi, and what that's referring to is just one of the 4 observations up here. So first thing we might put down are, well, we're following up the table, so we'll definitely put down 13 is just what would be referred to as y1. So we're really just saying what each part of the notation is really trying to convey. So y1 is the first observation, y2 is the second observation, or second individual in the sample. y2 is 15. Likewise, y3 is 19. And y4 is 21. So putting an I here is like a variable. It means we're talking about any one of the 4. I is just like a blank now. But already you might have noticed something about the data just by looking at the size of it, or this part right here. The sample size is n is 4. That's important to us because n comes up several places. It comes up here or on the right-hand side as well. But also we want to calculate the sample mean, which means we need the sample size 4 as well. We'll just do this one by calculator. To calculate the sample mean, our formula looked like this. Y bar is a summation of yi divided by n. That's a weird thing to look at, but all it was saying to do was add up all these observations, divide by our n value, which is 4. So let's write that out in the calculator. So let's go 13 plus 15 plus 19 plus 21. So that's all this weird symbol here is trying to say. It's saying summation of the yi values. We get 68. Divide by 4, which is our value n. So this just means add up. Then we'll just do that computation in your calculator. You can just immediately hit division, punch in a 4 and enter. And we have that y bar, the sample mean is 17. So we're on our way. That's 1 column down. And one thing we needed down, sample means computed. I think that's our second time doing it by hand. Any questions so far, folks? Getting that 17? Okay, so far so good with the numbers. Everything is coming out dead even. Nice integer 17. But that's where the y bar comes into play right here. The variance is going to be y1 minus y bar. Then we square that. y2 minus y bar, then we square that, and so on. You might have been wondering, why do we square this? It turns out without that power 2, the numerator goes to 0 every single time. That's kind of weird in a way. The deviations from the mean are yi minus y bar. Add them together without the power. You're doing the sum of the deviations from the mean. That's what this is saying right here. And they'll always add up to 0 exactly, unless we round it, and then it's really, really close. So let's see it happen. Deviations from the mean are going to be y1 minus y bar. y1 is the 13 to the left. Y bar is what we've calculated below, 17. And this comes out as a -4. Numbers are nice so far, but that stops being the case after a while. So yi minus y bar, we're just plugging in the I for 1, 2, 3, and 4 till we get to the end value of the sample. So now it's y2 minus y bar. So 15 minus 17 for -2. And if all you put in this cell right here is -2, that's fine. We're just putting in the actual writing here just to get a feel for what that is really saying. The best way to really read that and understand it is to actually just write it out a bunch of times. So next, writing this out again, and we're in row 3, is going to be y3 minus y bar. Y3 is to the left over here, 19 minus 17. Gives us a +2. And then one more time, y4 minus y bar. That'll be 21 minus 17. That equals 4. And sure enough, these things cancel in pairs, positive and negatives. It's a coincidence it went from -4 to -4, top and the bottom, -2, +2 in the middle. But what's not a coincidence here is that it adds up to 0. That's a weird mathematical fact already. So that means if we try to define the variance in a way that makes sense, the distance from all the observations to the center, that sounds like a distance. But if we never squared it, our variance would be 0 every single time, and that doesn't tell us anything about the spread of the data. So they had to do something fancy, and the next big thing was power 2. They didn't want to use absolute value bars because that turns out to complicate the math around our statistical procedures. Absolute value is more complicated than power 2, it turns out, which is a weird thought already. So we have all these observations, and this part right here is really just a check. The summation of yi minus y bar must be 0. Again, it's that same summation symbol, but it's just saying add all these up together. We just see visually it's definitely 0. If it's not 0, we've made a mistake and we ought to start all over. Maybe we copied something down wrong or subtracted wrong. Well, any questions so far before the next part of the formula? Okay, so the next big part, and this is necessary so we actually get some positive measure for how things vary or the spread, is this power 2 right here. So we're summing the deviations and, we're going to square the deviations, and then we'll take the sum. That's going to be the pluses or that summation symbol there. First, we're just squaring what's on the left. Instead of writing it all out, which is probably getting tedious at this point, we'll just square it. Negative times 4 times -4 is a +16. But this is a good opportunity to look at some crazy things that can happen in your calculator. Let me show you some stuff on this calculator that can be just like endlessly frustrating. Imagine you did put this in the calculator. Maybe it's -407 you're squaring. So we're all putting that in the calculator. In our problem, I go -4. This shows up and we didn't ever want that in there. We might try again. Something's kind of messed up. It's referring to a prior answer. You might even go 0 minus 4, but that's not helpful. Something's already kind of messed up here. You might try a parenthesis and go parenthesis -4. At least that answer thing didn't show up. So that looks pretty good. The power 2 button, you can either use the up arrow, or this is maybe a better go-to right here on the left. Kitty cornering up and left from the 7. Punch that and you get a power 2. And this doesn't work. It's frustrating. It looks exactly like how you might write it down on paper. Hit enter on that, and it says error syntax. It means the calculator has no idea what we put in here. You can either hit quit, that sounds kind of fatalistic, or go to. And if you went to go to, it's going to flash where the problem is. It's the negative. Well, the problem is it's a negative sign. Anyone happen to know the fix to make this work? Yeah, go ahead. Absolutely, good eye. That's the actual thing we want. This is a negative sign, meaning it's an operator that takes 2 values. There's no value in front of this negative, and we forced it to not take one. And so the calculator just doesn't know what to do. It's not going to put the 0 in for us. If you put in the negative like that, notice it's a little bit smaller. It kind of gets scrunched in, rises up a little bit closer to the 4, and that works. Hit enter here, and you get the positive 16 like we're expecting. So 16 goes in. I mean, we knew that. -4 times -4 is positive 16. But imagine this is a harder problem, maybe in MyLab statistics. This can be really, really frustrating. This is just for literal subtraction. You have two numbers. If you ever need a negative sign, it's got to be this. And there's more really frustrating things about this. Let me show you the next one. Any questions about this issue here? Okay, this next issue is kind of like an algebra issue. It comes up all the time. Even people taking loads of math, this kind of little mistake can crop into their scratch work. They meant one thing, but they wrote something totally different. I'm forgiving when I grade these things. I can read between the lines, but the calculator can't. It can sometimes feed you answers that are totally wrong for not being really closely paying attention to it. So we know we need to put in not the minus sign, the negative sign. There it is. Here's our -4, and we're about to square it. You can use the up arrow like that. Put in 2, or the shortcut like we mentioned. Let's use the shortcut like we mentioned. So -4 power 2. And then if you do this operation, it works, but it's the wrong answer. This is completely incorrect. Hit enter, and it's reporting a -16, and that's absolutely false. Negative times a negative is a positive 16. What was missing is the literal parentheses. You really have to write down parenthesis, negative sign 4, close the parenthesis. You might also tell yourself, if I'm squaring something that's negative, I don't even need to put that negative in there. I'm expecting positive already. But if we're putting things in the calculator verbatim, that's where it goes really wrong. Hit power 2 like this, and that's the correct answer. So watch out for that little algebraic weird oddity. If you write down -4 squared on paper, this is wrong too. I mean, we read between the lines on these. We know possibly what you meant to say. But what this is literally saying is shorthand for -1 times 4 squared. And in order of operations, exponentiation goes first. That's 4 times 4 for 16. Then it's multiplied by -1, and that's why the calculator gave us the -16 on here. Again, it seems like a small issue on this one, but it can crop in really big ways later on in the course. So what we need to say, let's just make a note. Well, it's not that it's incorrect, it's just not what we want. Let's say it this way. We want -4 squared like this one, because this literally means now in exponential notation, -4 times -4, which is the positive 16. And that's what the calculator is actually doing down over here. So that's a big spiel just to say, be careful with the negatives in the calculator. You can have perfect knowledge in statistics, and then sometimes MyLab statistics is just not accepting your word. Sometimes it's just because of those issues. Well, any questions at all, folks, about that positive 16 there? Okay, again, that's another purpose of doing this problem. Just getting familiar with the calculator, computing, and these weird oddities that show up. The next one we put in carefully, I mean, you probably did this in your head, but just to demonstrate, you might go -2 with parentheses, power 2, square it, and we get a 4. Another side thought, again, you're raising something to the power of 2. The negatives actually really didn't matter anymore. The negatives fall right off when you square -4, same with -2. But these are things that could be a bigger issue later on. Likewise, this 2 squared is 4. This 4 squared is 16. We've done squared deviations from the mean. That's this part right here. All we haven't done is sum of the squared deviations from the mean. So that's what we're going to do next. Finally, when we get to this part, the sum of the squared deviations from the mean, all of that is referring to S squared. That's this big formula down here on the left. In its expanded form, that's kind of what we've been doing tabular-wise. Let's use this part just to abbreviate. We're going to say S equals summation yi minus y bar squared divide by, not 4 this time, it's going to be the sample size 4 minus 1. So that's another weird thing about calculating the variance. If you're curious on why about that again, let me know and I can come up with some videos to throw onto the Canvas course page. There's lots of different ways to explain why that has to be the case. Well, back into the calculator, this summation part right here in the numerator, all we're going to do is go to the column above and just add these up. So 16 plus 4 plus 16 plus 4 gives us 40 in the numerator. Divide that by 3. Your calculator is already storing the 40. So notice when you hit division, A and S comes up again. That's the prior answer, 40. So just go division by 3, hitting this key and this key. That's a fast way to type things in, especially if the number 40 was like a larger number, maybe many decimal places. We get 13.333. It's set to round intermediate computations to 3 decimal places. So let's go 13.333. And we've done it, folks. We've calculated the variance. S, and I forgot my power 2 there. S squared is important to have that power 2, just as a reminder, because S itself is something different. And the variance is already a great way to measure how things are spread out. There's one big reason the book mentions that we don't actually use it a lot in these kind of settings. If the values here was in inches, we could say the center was 17 inches, but the spread would be 13.33 inches squared. The unit's different. That's kind of weird already. We don't want to describe the center in 1 unit, but how spread it out it is in units squared, that feels awkward. So that's one reason the standard deviation is just natural. If you take the square root of units squared here, you just get the same units. So if this data is in inches, so is the sample mean, it'd be 17 inches. And S, whatever it's about to be, would also be in inches. So we have 3 answers on paper. Let's maybe box them out just for emphasis. That was the sample mean. We just calculate the sample variance. Boxes are a good choice if it just feels like there's numbers floating everywhere. Last thing we do is calculate the standard deviation S. It says all you do is take the square root of whatever S squared was. Let's take the rounded value. And often if you're told to round in MyLab statistics, they're expecting you to use a rounded value on the next step. 13.333. However, if you use the exact value in the calculator on quizzes and exams, that's always okay with me. And oftentimes, MyLab statistics has 2 answers they're checking for. They're going to check if you take the approximation and do a square root here, and they're going to check and see how close you get to that answer. And they're also going to check if you just use the whole exact answer right here. So they're checking for a couple of things at once. So if you decide to be highly accurate, you would go like this. Square root is right here, but it's in blue, so that's kind of unfortunate. That just means you go second, hit the x squared button, and the square root symbol pops up. You might just type in 13.333, and that's always completely okay. You might type in 13.33333 and so on, just jamming that key. Or some people would do this. Up arrow, so it's highlighted. Hit enter, and it's just going to import it in. Either way you do it, sometimes it's nice to take advantage of those shortcuts. It can save you some time. And we're only meant to round this one to 1 decimal place it asked for. So I'll give it 3.7 on its approximation. So approximately 3.7. That deserves 1 more box. And we did it, folks. That's the sample's standard deviation, finally. Took a while because we're talking through it, but you can imagine if this was 12 numbers, and if you had a lot of decimal places right here, this becomes kind of a nightmare fast, where one simple mistake, maybe early on, throws everything completely off. So even if you do this highly organized, it's hard to get down perfectly. That's one of the reasons we're using the calculator, among many other reasons we'll see along the course. But again, this whole example right here is more just to show what in the world is this formula down here actually doing, because this calculator could be like a black box. We feed numbers and get numbers out. So the example above was to show you what it looks like when we compute those numbers. This example is to show you what the calculator is actually doing in fact. Also, just us getting used to computational matters at the same time. What, any questions at all, folks, with this quick rundown here? Okay, well, congratulations. This is not the funnest problem in the world, but it can be kind of relaxing in the way it's just numbers moving around. Problems in statistics get a little bit harder when there's context. And so that's what we're going to get into on example 4, the last one to end the notes. Before we do all that, I guess there's an example 3 I forgot about. But this one's just another kind of summary type of problem, just a roundup of all the statistics we have, their purpose, and when to use them. So probably feels like deja vu, but there's something new here. We did this in the last section with measures of center. Now we're adding in measures of variability into this at the same time with a couple more comments. So first, let's build our histograms to see what kind of quantitative data we're dealing with. For at least roughly symmetric, usually we don't want to make it look perfect because that's misleading. If it's perfectly symmetric, makes it feel like that's the only situation it works in. So we break it a little bit on purpose, just to convey that's all right. So here's my slightly asymmetric histogram. If you were bold to go maybe even this far, that's borderline at that point. It wouldn't be bad to leave on the notes. I'll leave it more like that. So roughly symmetric. Now picture for left skew. You can make this as left skewed as you want, but make it have no question about symmetry. Make it just very, very obviously skewed to the point of just looking kind of broken and damaged as data. So here's my left skewed picture. Looks like it's almost bimodal because it kind of came up a little bit here as well, but it has an overall skew to the left overall. Then finally for right skew, let's make this one look kind of more typical. You don't have to do yours exactly, so you can be creative on these if you like. But here's kind of an interesting right skew data. I don't know if we've drawn anything quite like this one where looks like half of something symmetric, but just the right half this time. No apparent outliers, but definitely skewing off to the right. Okay, so when it comes for our measures of center, let's just remind ourselves. Center, the major ones we're going to be using are things like y bar, the sample mean, m, the sample's median, and then when it comes to measures of variability or spread, we'll be dealing with things like S, sample standard deviation, or interquartile range. Doesn't hurt to write down the formula whenever you write down interquartile range, just as a reminder of what it is. 75th percentile value minus the 25th percentile value. So those are the things we're going to be filling in on this table down below. And I'll start off with row 1. The data is at least roughly symmetric. When it comes to the center, we prefer to use y bar, and we're pretty forgiving with this. Data has to really start looking bad before we decide y bar is no longer a good measure of the central value. We need the median m instead. Now, once we've made a choice here, it in fact immediately applies S goes down on paper. So big comment is already is that y bar and S, these go together. In other words, we would not mix y bar with the interquartile range. We wouldn't mix the median with the standard deviation S. We would put always these two statistics together when we're measuring center and then the variability. Does that make sense to folks so far with that first row? Okay, then last section notes 2.4 was the big comments that if you look at data like these, What happens with our center is y bar might be somewhere, maybe not quite that bad, but y bar might be somewhere quite clear out here, where the median might be over here to the right. The sample mean y bar got pulled in the direction of the left skew. On this picture, the median might be about here, and y bar might be about in that location. Skew to the right means y bar is to the right of the median. And in fact, the median is the better description of a central value. The central value is what we consider typical, and y bar is starting to get broken, become biased against the skew. When this happens, like we mentioned in the last section, we will use M in either case, skewed left or skewed right. These will be the best way to measure center. And for variability, same kind of comment. The median is linked now with the interquartile range. So in both cases, IQR. And same comment as below. These go together. Let's emphasize that a little bit better. Go together always. I think that's an important word to add in there. It's not as if the sample mean is y bar is no longer useful if you report the M and IQR. Still, it's a number. It can be interpreted. What we mean is the overall way we describe the center and variability is through those two measures and only those two measures. If we chose IQR, we've chosen M and vice versa. So that's our roundup of these statistics and how they relate to different shapes of data, like on the left. So far, chapter 2 has been a pretty long one. We spent like a day and a half in chapter 1. And then chapter 3 is going to be kind of like a day and a half as well. This book is kind of unbalanced with the amount of time we'll be spending per chapter. But before we go for just one more computational problem in the calculator, any last questions, folks, with any of these concepts? Okay, so one more computational problem, and then we'll be done with these notes here today. Here's how it goes. This is data from 2015. All my data is starting to look a little bit old, but not that old just yet. This one's called the 2015 Urban Mobility Scorecard. So for anyone in public works, this might be interesting to you. This is from the Texas A&M Transportation Institute, and it included data on the estimated cost in millions of dollars resulting from traffic congestion for different urban areas in 2015. Interesting name and actual date that turns out to be. I know we're lucky in Idaho, so we don't have any of the kind of issues you might see like New York, Los Angeles, and so on. So we get to see how lucky we are. It tells us next, the following data are for the 13 largest urban areas that have population over 3 million. So 13 largest, well, it means the sample size is 13. It also tells us something really important about these data. If this is the 13 largest, this is not a random sample. So already that's something to keep in mind. This is not data that's going to apply to every single large city in the United States of America because it's not representative of every large city in the United States of America. We just took the top 13 largest ones, and that's bias already. So that's something to keep in mind. It's rare to have data like this where it's specifically told not to be a random sample in that kind of way, but it's still interesting in its own right. So if you look from line to line, Atlanta is an interesting city. And this says in 2017, they have estimated, probably an interesting way they did this, that the city as a whole lost $3 million resulting from traffic congestion. So that's shutting down highways, repairs, it could be accidents, or just literal people jammed up in traffic. Some of the worst cases, New York City, that makes sense to be on the worst end. We're looking at $15 million lost. This is an economic monster, though, so I'm sure they made it up some way, somehow. But there it is. That's our data. And below is the histogram of that data. The unit here going horizontally is the cost of millions of dollars. And I didn't really see it standing out too much when I looked at the data, but it turns out these top two cities are kind of standing out now. They're separated from the pack by a distance of about 2 units as how these rectangles are plotted. It looks like between $2 and $4 million. That's typical of the 13 largest cities. That's just about where everyone is. So it says to us for the instructions, histogram of the data is provided below. Describe the shape of the distribution, and then we'll choose a statistic. It didn't say describe the shape using context, so we can be really brief on these. Would you all agree that we have skew to the right for these data? Awesome. We've been looking at skew for quite a bit, and the reminder is if you can visualize a slide and read it left or right, this is what the direction you're sliding off towards, or it's just trailing off in that direction. So we can say these data are unimodal is something we usually set first. So let's actually say that first. One make peak right here means that these data are unimodal, skewed to the right, and this does require a judgment call sometimes. In chapter 4, if you're curious, we'll get that rule of thumb. I think most people would agree those look a little bit odd. Would you all call those outliers in this case? Okay, I think we're getting pretty good at spotting these kinds of things when it comes up. Let's say that here once again. Skew to the right with 2 outliers. If these rectangles went here and here, and that rectangle is gone, then you know that's a judgment call. And if it was an exam question, I could see it either way. It makes it a bad question if it's kind of one of those things that's on the fence. You might say it does fit the pattern of skew to the right. There's not a lot of separation right here. And some people might say, well, but this one could be kind of far off, however. So when I write these on exams, I try to make it pretty clear cut. So if you're seeing how these go so far, we've looked at the borderline cases and the extreme cases. But now we want to describe center and variability for these data. So let's say here, for center, use for variability, or if you prefer, you could just call it spread. It's kind of nice to say it that way. It's really short. For spread, use some other one. This one, if it comes in as an exam 1 question and even a final exam question, it's honestly really kind of confusing what's being asked here. I'm not asking you to calculate the statistic. I'm really just saying, what's the name of the best statistic to use in this place? Anyone have a good name for the center statistic in this situation? What statistic would you say is best for the center? Should it be the sample mean or the sample median in this case? Good call. Here, just going to be the median. That's because it's skewed. So median would go here. Again, watch out for this question. It's hard to really write it in a way that's takes away all the confusion. Sometimes people will have just estimated the central value and said 3 million or 4 million. But here we're asking just the name of the statistic itself. So median is the answer to this kind of question. But once you said median, our hand has been forced on this one. It has to be the interquartile range because these are linked up statistics now. Median and IQR go together. And you don't have to say this part, IQR is Q3 minus Q1, but when you have to really think about formulas, get good using them, memorizing them even, not a bad idea to just write it down each and every time, just becomes second nature at that point. Sure, the exam does have a page of notes that you can bring, but writing down a page of notes means if you only wrote down that formula once, it's a hard formula to use actually. The more you actually write this down and actually calculate by hand, the easier it becomes to use. So that's not a bad habit to get into for certain things like these. So that's what part A looks like. And part B is asking us to actually compute this stuff. So these questions don't really go together too well when you think about it, because part B just sort of spilled the beans on the answer to part A. It says to calculate the median right away, and then to calculate the interquartile range. So these would probably be separate questions, really. Part of this question is right here. What made it hard is the fact it said using the context. Let me just target that better. So watch out for these questions on exams. You could lose a good amount of points, say in a 5-point question. That could be either 2 to 3 points out of that whole question, bringing in the context in our description. So while we're thinking about the context, good idea to just read it again. That can be really helpful on an exam or a quiz. So the reminder is all these values are millions of dollars of money lost due to traffic congestion in the top 13 largest urban areas in 2017. Now, what we do next is jam it all into the calculator. So I already kind of speed lined through that. The reminder on how this goes, and let me know if you get stuck at any step or if your calculator looks funny on your screens. First thing you'll hit is the stat key. It'll immediately put you where you need to be. So that's kind of convenient for our first calculator operation on exam 1. Hit enter just immediately on the screen. If you have a bunch of data, the things we mentioned is no harm is done if you just delete them one by one. It's just that it could take a minute. So if you get bored of that, hit up arrow, hit clear, and hit enter. And it brings it to this. So on exams, knowing how to use your calculator is part of the exam. If something goes weird on your calculator, like say if you deleted L1 on accident and now you're not sure what to do, I can help with technical issues like that on the exam. So if your calculator is just on the fritz, but you know how to do everything else, like put in the data and get the statistics, I'm able to help with the weird parts. Something just doesn't look right. And if I can't fix it, I'll just hand you a loaner calculator that usually does the job as well. So let's just put in these numbers. I'll just go down the line and go quiet while we're all putting these in. This is what messes me up. There's 1, 2, 3, 4, 5 fours. Okay, anyone need any more time on this one? Okay, after that's done, hit the stat key just again. So we just end up jamming that key a lot to get started. Once you right arrow, if everything's set up, all you're now doing is jamming the enter key a bunch of times. Your screen should look exactly like this after you hit the right arrow. Then let me just do that. Enter, 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 and all this comes up. So I got 5.6923. Anyone get about that for their sample mean? Okay, it's not what we wanted, but that's just the check we agreed on our data entry. Now, to get what we do want, go down in the bottom here. And first thing is the median value. That's the one that's MED in the calculator. I'll just leave it as M. No harm done if you did write out median or MED for short. So I'll write out 4. And that seems kind of uncomfortable because remember, the unit is actually in millions of dollars. So some people might just leave a 4, which is fine. Some people might actually go 4, put in the actual 6 figures. Either answer is just fine because when we explain what it means using the context, we'll explain that number better. So I'll just match up what the calculator gave us. and then explain the number better with the context. Now, next one is IQR. I'll just use a 2-column system on this one. Here's where the formula comes into play. So quartile 3 minus quartile 1. Quartile 3 is this value, 6. Quartile 1 is a value of above, 3.5. So we'll get here 2.5 for our IQR after subtracting those numbers. Any questions, folks, using the formula here? Okay. Yeah.
So it's Q3 minus Q1, but if you scroll back up to when you made the dots on that one.
Oh, on the paper. I was scrolling on the calculator.
Sorry, yeah, right there. It says Q is. So
Oh.
we ever have to mark it?
Yeah. That should have said Q1 right here, not a Q2.
Okay.
Yeah, that was my mistake on that one. That was odd. Let's fix that for the record right here.
Thank you. I'm not sure if we're gonna have to mark them on the histogram or not.
Probably not on exams. This is more for our visual, seeing what they mean. But that is extremely confusing because it's the median is the one that's actually Q2 is what that one's referring to. And this is Q1, that's Q3. Who knows? Probably was micro sleeping when that came in. Thanks for spotting that one. Other questions at the moment? Okay, so we've got our two values down. Now here comes the tough part. We have to say what they mean. Let's maybe start with the median value. I think the interquartile range is a little bit harder. So good exam strategy is go for the low-hanging fruit. Complete the things that make the most sense. It lets your subconscious work on the harder problems. So let's start here. Interpret the median value using the context. This was the 13 largest urban areas in the USA. So we can say, you might say the central value, or you might say the 50th percentile. You might just literally say the median, and I would say that's okay. But if you really want to interpret the values, I think a better word here would be the 50th percentile from money lost to traffic congestion for the 13 largest urban areas is $4 million. It takes about as much time as writing $4 million as it does putting in the dollar sign and all those zeros. And this is not the entire context, right? I didn't say that this was 2017 data. I just left that up there in the context. So when I say using the context, I don't mean you have to scrape every single fact that you saw up there. Just try to get to the main parts. If you left a couple things off, that's okay. If you didn't say largest urban areas, but you said 50 percentile from money lost due to traffic congestion is $4 million, and that was it, I would say that would qualify for a full credit response on exam. You saw the context and you rewrote it here. We put in two elements, that it was traffic congestion, and this was largest urban areas. Does that make sense to folks on writing down this one? Okay, this one's harder, and that's kind of the reason why we took all that extra time of just writing this down on paper. Let's go up back here again. Again, thanks for correcting the units right here. That was going to look funny when we come back to it. When you're going to interpret the interquartile range, you can just literally say it's the length of the central 50% of observations. Just throw in the context and you're always okay saying that because that's exactly what it is. You could say 50% of the observations go from 3.5 million to 6 million. If you did that, I would still say, yeah, you're talking about the interquartile range. You just gave me the two numbers. So that would be an okay way to say. Some people really like saying those two numbers. They would say the central 50% of all observations for money lost is between 3.5 million and 6 million. But if we're following it to the letter, we're interpreting the range. Let's go with that route. So there's lots of ways to answer this correctly. For this one, we can say in 2017, the range for the central 50% of observations is $2.5 million. And it feels like I really left off a lot of context on this one, right? I brought in the year, and I brought in the fact that this is dealing with money, and we just said what the interquartile range does generically. It's how long the central 50% is. But you know, this is really appropriate on an exam as well. You told me a bunch of context over here. We all know that it's the same context over here for the interquartile range. We didn't change the problem. So this can carry over. You don't have to say everything twice. If it feels like you're being redundant, you really don't have to. I mention all those things because when I say I'm trying to write a 50-minute exam, that just depends on how much you're writing. So I'm trying to give you some ideas of you don't need to give me paragraphs on every problem unless you had the time to do so. So you might answer this quickly, maybe come back to it and see what details you want to add. But anything folks feel like they would want to add to any of this so far?
It doesn't seem right to me that you leave off on the quartile range.
The 6 and the 3.5?
Yeah.
That's more information. Yeah. Once you say $2.5 million, well, on what end did that $2.5 million occur? I agree with you. So a lot of people would prefer to actually mention this. It still gives you interquartile range and the actual information of where did it go from. It was from the 3.5 here up to here. So yeah, I think that's a great answer as well. We followed it to the letter and just used the 2.5 millions. But let's add that in. These,
as we get later on into doing this, is that, I mean, is it pertinent to add those?
I would say for the sake of giving an interpretation, yes. In chapter 5, we'll be using the interquartile range in this form. So we're really just going to use the number 2.5 more often than not.
Perfect.
But yeah, for interpretation, I agree with you. We actually deleted information by not mentioning those two numbers. So let's throw it in. These central values ranges from 3.5 to $6 million. If you gave me just this part, the central values are from 3.5 to $6 million. Again, that's good enough for me. That is the interquartile range. It's just a subtraction away. If you took it to the letter, interpret the IQR, it would have been this part. You just have said 2.5 million. That would have been all right as well. So it's a lot of times a judgment call on these kind of problems. If you're doing an exam question, what you said is right, you brought in the context, you're almost certainly going to get the right credit on this, the full credit on it. If things missing or if something's untrue or there's no context whatsoever, then that's where you're going to start losing points on that kind of question. But any other questions or comments? Anything further folks would like to add additionally? Okay, well, we ended on time this time, just barely. When we come back on class, we'll be in chapter 3. And if you have time to do pre-reading, just a warning, we're not going to cover all of chapter 3. We won't be using everything in that chapter throughout the course. So the reading is just going to be the first two subsections, 3.1 and 3.2. But have a great night, folks. We'll get back to it on Wednesday. Oh, and maybe one more reminder, that's the last section that's actually on exam 1. So this is exam 2 material coming up next.
but we won't have a chance to get our, or no, we will, right? When we get our quizzes back from this week before the exam.
You'll get your quiz two back, absolutely. And then, yeah, so your quiz two, hang on. Yeah, you'll get your quiz two back because what I do with the exams is that once I have them graded, like this file here, I'm going to send your graded quiz to your ISU email address. So you'll get it back in that way. And the thought I was getting mixed up with is I'm posting a third quiz as well.
Okay.
It'll be on the exam material, probably based off 2.5. If you want to solve that early and like take a picture of it or scan it and send it to me, I'll grade it early as well and send that back to you. So you'd be working a lot faster on the due date on the third one. So it's up to your option on that.
Resources for school nowadays is nuts.
It's definitely different from when I took this class even. I took this class in like 2006 and there was a lot of stuff on the chalkboard. It was weird.
That's what blew my mind the first time I seen you doing this and like saving the notes. I was like, this is crazy.
Yeah.
It's almost like cheating, it feels like.
But what was crazy too is it took the teacher a long time to just copy down a problem on a chalkboard.
Right.
I spent a lot of my life just watching people drawing on there, getting chalk on their nose. So I don't know if that was the best use of my time either.
I wasn't sure if the technology and stuff, because I'm super old, but I'm learning computer and technology,
Mhm.
but it really is beneficial, you know?
Yeah, used right. I think it's easy for it to get like kind of just overused, put too many bells and whistles, and then somehow you're cheapening the whole thing.
I think it's pretty cool how you color code. It makes it really easy to follow along.
Yeah, connecting the dots is huge with this kind of stuff, I think. And color code helps a lot.
You have a good night. See you on Wednesday.
Yep, take care. I forgot he was even in the class. That's awesome. My dog would have been pissed off 5 minutes in.
Are you okay if he's here on Wednesday and Thursday too? I just have him for the week.
Yeah, that'd be totally fine.
But,
Sounds good.
sorry,
No worries at all. Very well behaved dog.
yeah.